Good afternoon. Welcome to Krishna's class. We begin with another talk on LP spaces. Continue from where we left last time, but before that, maybe we recall the notations so that you are comfortable while following this talk. So we had X mu as a measurable, as a measure space. LP mu was defined as the set of all f, which is complex valued and measurable, with the norm f p less than infinity for 1 less than or equal to p less than or equal to infinity, where norm f p was defined in two different ways, namely norm f p was integral, that is, it is pth power is see, norm f p was, okay, let me just write here, equal to integral over x mod f p for 1 less than or equal to p less than infinity, and for, see, norm f infinity was defined as essential supremum of f for x belonging to, this was the definition for norm fp, and LP consists of all those f which are complex valued and measurable, and norm fp is finite, and we proved that norm fp defines a semi-norm. In fact, it falls short of being a norm. I mean, it doesn't assure you that norm fp equal to 0 implies f equal to 0. Now, this is the shortcoming of that. And then we can define all other conditions of norm are satisfied. Again, on LP mu, we can define dpfg by, that is the distance from f to g, by norm of f minus g, which defines a pseudo-metric on LP. And LP mu, we had shown that it's a linear space, therefore all these operations are sensible. Okay. Now, therefore the problem was the norm fp is a semi-norm, therefore LP norm p does not define a normally linear space. It is a semi-normally linear space. Fall short of that. Similarly, dp as defined here in terms of the norm, because every norm induces a metric. Here it is a semi-norm. Therefore, once again, the handicap that you have for norm fp to be a norm is carried over here also, because dp is defined through norm f minus g as defined as norm of f minus gp. Therefore, that shortcoming is already there. So, you cannot say that dpfg equal to 0 implies f is equal to g. That statement is not possible. Therefore, it's again falls short of being a metric. So, it is called a pseudo. Now, this kind of situation quite often appears in the in analysis. Okay. Therefore, we observe that one can define a relation on LP by f is related to g if and only if norm of f minus gp equal to 0. Now one can show that this is an equivalence relation, satisfies all the three requirements for that, namely reflexivity, symmetry, and transitivity. Therefore, what it does is it induces a partition of LP into equivalence classes. That means, well, that is a very general theorem. If you have a equivalence relation, then it induces a partition on the set and gives it as a union of, or represents it as union of disjoint boxes. Now that is the advantage that. Okay, so we designate LP tilde mu consisting of all those elements of the form. For instance, we use the notation bracket F denotes the set of all G in LP mu, which is related to F in terms of this equivalence relation. Okay, so you know that if you take two such elements, say F and G, F is either, you take two elements F and H, then either F is equal to H or F intersection H. Now this is the scenario that. Okay, right. So LPW is the set of all boxes F, boxes consisting of F, where F belongs to LP. Now we show that this defines a vector space. So we have to say what exactly is addition and scalar multiplication. And we define it as follows. Box F plus box G is identified as box of consisting of F plus G. You can show that this is unambiguously defined in the sense that if F1 is another, box F1 is another representation for F and box G1 is another representation for box G, then box F1 plus G1 is essentially identical with the box F plus G. Now that you can show, and then scalar multiplication we define for alpha belonging to R and F belonging to LP, and the box F belonging to LP tilde, we define it as, identify this as the box alpha F. Okay, once again you can show that this is unambiguously defined. That means it is independent of the representation that we use to represent these boxes. Okay. Further, you define, therefore you have now a linear space and all other conditions of LP tilde being a linear space are satisfied. So that can be easily verified. Now define the norm of box F designated by norm P of box F is defined as the norm of FP. Now this we already know what it is. Similarly, and you can show that this is a norm. This is a norm. Earlier we said that if you use this on LP, it becomes a semi-norm. But now on LP tilde, this induces a norm. Because you see that if you have, so this means the following, if this property is the zero element of LP tilde. So this property is satisfied. Now this is what we can show. Therefore, this defines a norm. All other properties are satisfied that we have verified out. t. Similarly, dp fg is defined by norm of f minus gp for every box f and box g belonging to lp tilde. Then lp tilde norm p is a normed linear space. Similarly, lp tilde dp is the corresponding metric space where the metric is induced by the norm. Okay, so this much we have already done, and the details are there in our previous lecture. So now you see, hereafter we will be working on the normed linear space, not on the semi-normed linear space. Therefore, what we do is, henceforth, instead of every time putting this tilde on it and then bringing the box in our writing, just to avoid that, we designate henceforth LP tilde mu tilde or LP mu tilde by LP mu. Now this is an important thing, don't get confused from now on. So from now on, whenever we write LP mu, it means it consists of all the equivalence classes of components represented, determined by the various elements of that. I have already shown that this is a metric. So instead of LP tilde mu, we designate it by LP mu, and further we designate box F by simply, so whenever we write F, it means box F, because we are working in a new space. Now probably a small diagram will because it's a very important concept we often use. I said that this kind of concept is there when you try to define what is called from fractions. You determine what are called, or you define what are called the rational numbers. In that context, we use this idea. Okay, so the idea is this: you have got a set LP mu, then you have the equivalence relation. It partitions this whole space. Now this is F, this is G. When F is here, G is here. But if G is inside this, then box F is equal to box G. Okay, so that's the idea. So these are the things. So it's on a new class of objects that we are introducing the norm, and this becomes a norm space. Okay. Here, once again, I want to say is the following. See, whenever you say the following, see, that equal to 0 for F belonging to our old LP, that means the original LP, then it means is equal to 0 almost everywhere on X. Not everywhere on X. That is the problem. Okay. Therefore, now in the new as small f equal to 0, which is the zero element of LP tilde. Okay. So we have now in the new redesignated version f equal to 0. In the redesignated form norm of f identically 0. So this is the new scenario. So just don't get confused with the notation. Henceforth, whenever we are talking about LP mu, you mean the elements are not simple LP functions, but the blocks of LP functions which are related to one. So that much you bear in mind. Therefore, henceforth we have a normed linear space and a metric space. The norm introduced by this is the norm that is given. dp is defined as so this is the nature of the normed linear space and the induced metric space. Okay, so now we are ready to work on this. Okay, why do we? Okay, so what you have now on LP, now you have a new structure, namely a topological structure. Therefore, now you can talk about functions defined on this or from this topological space into another topological spaces and have all sorts of topological properties looked at for the functions. Okay, so that is the scenario now. Now what you have is, so you have mu v and you have LP mu v. So the induced spaces. Okay. One is the normed linear space and this is the induced metric space. Okay. So if you want to do further analysis on LP mu, you should have concepts like convergence and so on. So we can explore such concepts on LP. So we will first introduce what is called convergence. Let be a and these are all boxes actually, equivalence class of elements in the original. Okay. Now we say that the sequence Fn converges to F belonging to LP. If it does, this is not something that can be assured at the moment. if given epsilon positive, there exists an n which depends on epsilon such that norm of that is dp of fn f is less than epsilon for every n greater than n epsilon. This is the usual definition of convergence. Okay. So there is no guarantee that at the moment that given a sequence fn in LP it converges. So that is not there. Okay. And because we are not assured at the moment that there will be some element in LP to which it eventually get closer. Okay, so that is not something that is assured at the moment, but we will explore this problem now. So we shall define something related to this, namely Cauchy sequences, which you already know. Fn, a sequence Fn belonging to is said to be a Cauchy sequence if given epsilon positive, there exists a n epsilon depending on epsilon such that norm of so what it says is that for any epsilon positive, there is a corresponding integer n such that the p norm of fn minus fm is less than epsilon for every n and f greater than or equal to n epsilon. Conceptually, this means, I mean, we have already seen this in many places in the general context of metric spaces. Now, this, you know, this is essentially dp fn fm. Okay. Now, you see that this implies that as n and m gets larger, okay, the distance between them gets smaller and smaller, as small as you want, as you please. Such a sequence is what you call a Cauchy sequence. For instance, look at the sequence, consisting of say, for example, 1 plus 1 by 2, comma 1 plus 1 by 2 plus 1 by 3 factorial, etc. This is a sequence of rational numbers. The general term is sigma n k equal to 0 to n 1 by k factorial. This is the nth term or n plus first term that you. Okay. Now you see that this sequence is a sequence of rational numbers. But these rational numbers, as n tends to, given epsilon, you can find a n such that the Sn minus Sm is less than epsilon for n and m greater than some n epsilon. This is possible. So this is a Cauchy sequence. Okay. So this sequence is a Cauchy sequence of rational numbers. but it does not converge to a rational number. Okay? The limit of this is not rational. The limit of this is essentially E. This actually converges to E, and E does not belong to. So a sequence is a Cauchy sequence does not imply that the sequence converges. Okay? It may converge or may not converge in space. That's a property of the space. Okay, whether this happens or not. With Q as a subcollection of R, Q is a metric space with the same metric as you use on R, but you cannot assert that in Q all the Cauchy sequence of rational numbers is convergent in that space. Similarly, one of the problems that you encounter here also is this. Given a sequence Fn in LP, you ask the question, suppose it's a Cauchy sequence, is it possible for you to assert that it converges? Okay, right? See, in the convergence we said that converges to F if something happens, provided it converges. There may be a Cauchy sequence which may not converge at all, as you have in the case of Q and R. Okay, so let me just, these are all very routine things. But if the space has the property that all the Cauchy sequences in that space are convergent in the space itself, then you say it's a complete digit space or a complete norm-digit space and so on. Okay, right? So the question that you ask is this. So one of the immediate questions that you ask is this. Do all Cauchy sequences converge in L? This is a question that you want to settle, and that is going to be the theme of our talk today. What does this mean? This means you start with any Cauchy sequence of functions in LP. Do they converge to an element which is again in LP? Okay, this is the question. If you are assured of all these, if you are assured that all the Cauchy sequences in this space converges, then you call this space, give this space a attribute, namely the space is complete. If does, then we say that the space is complete. So the completeness of the space is what we are after. Okay. So reframed, this question is LP complete? Is it a complete metric space or is it a complete normed linear space? Now, why are you after this completeness? We are after this completeness, or we want to make sure that the space is secure to do analysis on it. What do you mean by that? Suppose you choose a function which chases suppose you have something like this, a function which chases this a Cauchy sequence. The question is that whether you run outside the space by chasing it. If you do, at least for all reasonable type of chasing, okay. So in short, see, it's like playing a game on the of football on the deck of a ship. Okay, the deck has no wall. Okay, and you are chasing a ball on the deck. What will happen? You may end up falling into the water. Okay, if there is no wall. So the question that you are asking, is there a preventive wall for your space or another space? In other words, every time you chase a Cauchy sequence, you are assured that it will stay within the space itself. Now this is the problem that we are talking. So to assure that, the property that you need is that the space is complete, or every Cauchy sequence has a limit within the space itself. So let us formally define this. Complete metric space normed linear space, complete normed linear space if every Cauchy sequence converges in, you don't have to search for limits outside this space. In the space itself, you are assured that there's a limit. Okay, this concept is what you call completeness. And in that case, you say this is a complete metric space or a complete normed linear space. Here, of course, you are working on a linear space. That is why you talk about normed linear space, etc. But in general, you may have situations like this. X, D is a metric space with no structure on this. Okay, once D is there, you can talk about distance between two elements, and you can talk about sequences or Cauchy sequences. Then you can ask the question whether every Cauchy sequence converge in this space. If it does, you say X is a complete metric space. Okay, but here there is the additional structure that it's also a normed linear space. Therefore, you use the terminology that it's a complete normed linear space. This is generally known as Banach space. Okay, right. So that we shall not see at the moment. Okay. So the central theorem that we are going to prove is NP is complete. It's a complete normal linear space. It's also a complete vector space. Now we give the proof. Split the proof into two parts. One, first we assume now let me just give some more things about this. Suppose you take CAB or C0. Suppose you consider C0, that is the set of all continuous functions defined on the interval 0, 1, and with the usual method. Or the L1 method. What is that? That is norm of F and this is L1 method. And this is L1 norm and D so what we can prove is that C what does it mean? It means if you take a sequence, there exists, that is, there exists a Cauchy sequence in C01 respect to norm 1 a continuous function. Now this is geometrically very easy to see. So you take this is 0, 1, half. Now you take Fn to be so you take the function to be identically 0 here and then over here take the function to be 1 over here from 1 by 2 plus 1 by n to 1 and in between it is patched up continuously between 1 by 2 to 1 by 2 plus 1 by n and call this Fn. So Fn is defined as identically 0 from 0 to half and equal to 1 from 1 by 2 plus 1 by n to 1. In between it is linearly patched up. It's a continuous function. So each Fn is a continuous function. Now you can show that such an Fn is continuous by definition. Fn is Cauchy in L1 norm and but the limit is a discontinuous function in fact the discontinuous function is the discontinuous function f1 fx equal to 0 on of and equal to 1 for x belonging to after. Okay, so this is the function that you have. The limiting function is something like this. See, it is 0 here. On this portion it is so. So this is the limiting function. So that limiting function is not a continuous function. So just keep this in mind, and that is to show that there are spaces which are not where the Cauchy sequences do not converge to an element in the space. So we see that C01 with L1 now is not complete. Okay, therefore that is the conclusion. Now we can return to our problem. Okay, that's an example. So that's a slight digression, which is worthwhile digression to highlight a point. So we assume 1 less than or equal to p less than infinity. We shall take up the case p equal to infinity separately. So we have the assumption 1 less than or equal to p less than a. Now what we want to say is LP is complete. LP is complete for all p, for each p lying between 1 and infinity, 1 less than or equal to p less than t. So that's what we want to prove. Then let us prove this. Okay. So how do? We start with a Cauchy sequence. Let Fn be a LP. Now, what you can show is that, what does it mean? Given epsilon positive, there exists an n epsilon such that norm of so this is what you have. That's the meaning of that. Consequently, what you can do is, see, we extract a subsequence from it. We choose a subsequence. As follows. How do we do that? Say, denoted by FNK. How do we pick this subsequence? How do we do this? Such that the following is true, namely n1 less than n2 okay, and norm of f n plus I, sorry, n I plus 1 is less than, sorry, minus f n I is less than 2 to the power minus I for I equal to 1, 2, 3. This is possible. Why? Because the first epsilon that you try is this. Okay, use I equal to 1. So you take epsilon 1 equal to 1 by 2. Then what you have? There is an n1 related to 1 by 2 such that from fn1, f capital N1 onwards, all the entries, all the elements have the property that the distance between them, between Fn and Fm, is going to be less than 1 by 2. Okay. Therefore, it is quite easy to pick one element from that as Fn1. Okay. Right. So you choose Fn1. Second stage is what? Take I equal to 2. In that case, you are choosing your epsilon 2 equal to 1 by 4. Now, once again, there is an n2 associated with it, such that norm of Fn minus Fm is less than 1 by 4. Okay. So you see that this f n1 may be in it or may not be in it. You don't bother. But you choose now an Fn2 which follows Fn1, okay, which appears after Fn1, and such that the particular condition is satisfied. There are plenty of elements from which you can pick one of them. So there is always such an element. Therefore, you have, or 2 also, you can find an element. In that way, we can construct a sequence Fnk. Fnk is constructed with this property. Such a sequence exists. Okay. Now define Gk to be equal to sigma I equal to 1 to k f Ni. Okay, so GKX you are taking as this one. Okay, and we take G to be infinity okay, so this is one. Therefore, by 1, what happens? See that mod Gk is less than or equal to, is bounded by the sum of this. Now, each of this is less than or equal to 1 by 2 to the power minus I. Therefore, it's a series that you get of sigma 1 by 2 to the power I, which converges. Okay. Therefore, it is bounded by that. By 1 and by the Minkowski inequality, we have by Minkowski inequality we have you see norm of Gk is less than or equal to and each of this is less than or equal to 1 to infinity, and that converges. Okay, and this is okay for k equal to 1, 2, 3, etc. So that is true. Having got that, our next task is this. By Fato's lemma, applied to is norm of okay is less than or equal to 1. In particular, is less than infinity almost because you are making an assertion with respect to the norm P. Therefore, all that you can say is that GKX is finite almost everywhere. Now, this is an important inference that you make. Now you look at the series. This series you take. Okay. Now this, let us designate this condition by 1, 2 and this 3. Now this series converges absolutely for almost that means except possibly on a measure set of measure 0, this converges. So let us designate by sum. In 3, wherever it converges. And take fx equal to 0 on the remaining set of points x, the remaining set of points on x whose measure is 0. Because we have seen that it converges almost everywhere, and the complement of the set on which it converges has measure 0. That is the meaning of that. Okay. Now we note that if Ni equal to Fn. This is just cancellation that takes place. Note this way. Consequently, we have fx equal to fx that we have defined there is equal to limit I tending to infinity f ni x for almost all is almost every. Thus we have produced a function. So we started with the sequence Fn, constructed a subsequence with certain properties, and now we have proved that this sequence converges to a function f almost everywhere. Okay. Identified a function f which is the pointwise limit of Fni we now prove that f is the LP limit of that means in the LP now Fni converges to f. Such that this is merely the restatement of the fact that Fn is a Cauchy sequence. Okay. Now for every m greater than n by Fato's lemma we have integral over x is less than or equal to lim in, this is just the application of Fato's lemma, infinity, integral over x and you have an estimate of this, and from that estimate it would follow that this is less than or equal to epsilon to the power Okay, it follows from the estimate of this that you have. Okay, right? From 6, it follows that FM converges to LP, EA, and this would follow from the following property, that F is equal to minus Fn. Apply on this. Okay, and norm of goes to 0 as both these inferences you can make from 6. Okay, so that means they'll be no. So that completes the proof. So this completes the proof. For infinity. So the first part is done. Now we have to take up the case p equal to infinity. Okay, let me just leave it at that. It is incomplete still. We have to prove the case for p equal to infinity. We'll take it up in our next lecture. Thank you very much.